Hands up, who did go to my previous talk? Half, maybe. Okay, great. Thank you for... This one is not meant to be a continuation or anything like that. In fact, I shouldn't be doing 2 talks. I only signed up for one, but they had someone drop out of the program, so I agreed to repeat this talk because I gave this at GopherCon US in San Diego last year. And so I have to say, this is already a much nicer audience, or better for me anyway, because I don't have Russ Cox sitting there. No offense, but slightly tension-inducing. Anyway, so this talk is about algorithm, or about one algorithm. So who likes algorithms? Okay, a few people. Okay, you're in the right place. Who's like studied an algorithm outside of university or job interviews? Wow, there's even a few people claim to have done that. Really, it's job interviews, right? As was mentioned, I work at Grafana Labs. I work on the storage of metrics, logs, and traces. And this algorithm is used in most of our databases now. But it's kind of a voyage of discovery. I want to tell you some things I learned, and maybe you can learn something along the way. So here's the outline. Oh, if you want to find the code, I have a QR thing. It's on GitHub. So there's the problem that we're solving in this algorithm is called the k-way merge problem. We'll talk about that. The algorithm is called the loser tree. I mean, basically, the minute I read the name, I had to give this talk. That's the way I feel about it. We're going to talk a little bit about profiling and benchmarks. So not too, for those of you who, I did a talk earlier about profiling and benchmarks, so we're just going to have a little bit of repeat there. But even though what I signed up to do was a repeat of last year's talk, there is bonus content. You will receive unique additional material in this talk. Okay, so the story begins with a flame graph, a profile. So I'm not going to spend too much explaining what's going on here, but basically when you look at these things, the wider the bar, the slower it is, the more time it's taking up. And so this is a real profile that someone sent me because they were complaining that something was too slow. And it is on flamegraph.com, which is shows you these pictures. You can upload your own flame graphs to flamegraph.com, your own profiles, if you want to share them with your friends. The point being is a tremendous amount of time being taken up in this thing called heap.fix. Can you? I need the mouse to be here for you to see it. I mean, it actually shows up twice for reasons, but like 12% or something like that of the whole program time was spent in this heap.fix routine, when the total time 3.43 minutes. This is a 30-second profile. This is the standard length of a profile. So this is 7 CPU cores, of which a decent chunk is spent in this one function. So what's going on? So this is an algorithm called a heap, where it's used for priority queues to keep like the highest thing or the lowest thing at the beginning of a slice. And in Go, Where is my mouse gone today? Oh, well, I'll just talk. So in Go, it's coded with an interface, and it has these two methods, less and swap. And basically, the overhead of calling through these indirect methods on the interface, the overhead of having Go figure out dynamically what this thing is and go off and do the thing, ends up being tremendously expensive in the inner loop of this algorithm. So this is the interface of a heap. How things have to compare against each other, one less than another, and things have to swap in the array. Without getting into too many details, I decided the reason why it was slow is it's calling these methods indirectly. Dynamic dispatch is quite slow. And I thought, can I use generics? Can I, this is a couple of years ago, generics was relatively new. Can I use generics to do this without dynamic lookup? Well, hold that thought. I need to explain what we're doing. So to illustrate, we have 4 sequences here, sequences of numbers, just using simple numbers to talk about this. This is the k-way merge problem, 4-way in this case. So I have 4 sequences of numbers. Some of them are different lengths. They all have different numbers in. They are all individually in order. And I want to end up with one sequence which has all the numbers in order. So that's the whole problem that we're trying to solve. So we start with the lowest one. Okay. Then we take the next lowest. And you see the sequences kind of bump up. Every time I take a number off a sequence, I get the next one, and the next one, and the next one. And there we go. So, cool animation. Right? There's a lot of animations in this talk. There's no live coding, which makes it a lot more relaxing for me. Okay, so figuratively, that's what we want to do. How do we write an algorithm to do this? How do we pick the smallest one every time? Well, this is an extremely well-studied thing. There's a whole Wikipedia page on the k-way merge algorithm. And halfway down the page, it says to use a loser tree. It's actually on the Wikipedia page. So like I say, at this moment, I saw myself giving this talk. So what is it all about? So there is actually a pseudocode implementation of the algorithm on the Wikipedia page, which does not work. So I had to figure it out some other way. I went to my copy of Knuth. Who's read the Knuth? I'm not going to put my hand up. I own 3 volumes, but I've not read all of them. But there it is, a tree of losers. This is followed by about 60 pages on how to do this efficiently using tape drives. Because this book is from 1972. And so that wasn't entirely useful, but still, Don explains it all. So let me tell you how it works. What we're going to do, taking my same set of 4 sequences, I build a tree. It's a computer tree, so it grows downwards. We build a tree out of the numbers in the sequence. So let me show you how that works. So the first step is to fill the leaves of the tree, when we just take the first number from every sequence, right? So those are the leaves of the tree. And now, so the other name is tournament tree. So it's like a tennis tour, Wimbledon tennis tournament or something like that. We're gonna play matches between the two contenders at each point in the tree. So we start off, we do 2 plays 5, right? Go on. There we go. Fight. Okay. So we're picking the lowest every time. So 2 is the winner, 5 is the loser. We store the loser in the tree. That's where it gets its name. 3 versus 4. 3 wins. Okay. And now we do the same thing at the next level. The winners play each other, because that's what happens in tennis. We've stored the loser. We're not going to look at the loser anymore for this round, but we play off the winners. And then we have the overall winner of the whole contest, which is the first element we need to pull out of the tree in order to do our merge. So we've populated the tree. We're going to start pulling things out. So pull that 2 out, and the next number pops in where the 2 came from. And now we play again. We just go up the tree this time. 7 versus 5, 5 wins. 5 versus 3, 3 wins. We store the loser every single time, and then we can pop the winner off the top, and another number comes into the tree. Keep going. 6 plays 4, 4 plays 5. 4 is the new winner. Play those ones up the tree. And at this point, something interesting happens. We've popped, this sequence is completely empty, where the 5 came from. So what we need to do is put infinity in that space, because we want everything to win against this number. We don't want empty space to win in our contest. So we put a, I mean, in practice, it's a number higher than all of the ones you're ever going to find. So then keep going. Infinity plays 7. Infinity is the loser. And we pull 6 off. And so yeah, that's the loser tree algorithm. That's the basic pattern of how it works. And it does work. Well, it's in Knuth, so it must work, right? Okay, how fast does it go? Well, let's start with the algorithmic complexity. So basically, every time we pop a number, we have to go up the tree replaying the games. The number of steps in the tree is the logarithm of the number of elements, or the number of sequences, rather. Not the number of elements, the number of sequences. So in this case, I've got 4 sequences. I've got 3 levels in the tree, and so that's, let's do that. N is the total number of all the values. So to initialize the tree, we do k-1 comparisons. Each player loses 1 game in the tournament. And as we go up the tree, it's log k comparisons. So the overall algorithmic complexity is k-1 plus n log k, or basically n log k is the algorithmic complexity of this thing. It's linear in the number of elements because we have to pop n elements off, and it's logarithmic in the number of sequences because we do log k comparisons every time we go up the tree. That turns out to be the same algorithmic complexity as heap, as the this sort of standard way of doing it is to use a heap. The algorithmic complexity is the same. But if we look at how it's implemented, we can get to why am I excited by it? Why am I interested in this thing? Why did I think you would be interested? Okay. So the package is called loser, so I can have loser.tree. The things that are stored in it, I've put a type in called value, but basically it's constraints.ordered. So this is things like integers and strings, things that I can do less than on is that type. I have a type which is a sequence of those things, which has two methods. One says at, and one says next. And we build a tree out of nodes of those things. So it's using generics. It is, I've got a note to myself. So this constraints thing is comp. So I wrote this talk before this went into the standard library. That should be CMP, and I forgot to update the slides. But anyway, the ordered type. And it is using generics. So got that bit that I wanted. This is our abstract visualization of the tree with the nodes that we're dealing with, and I've added a sort of 0th node for the winner at each stage. Get ready for this. Did you get it? Took ages. So this is a tree formulation in that in order to get to the parent node, I divide by 2. So like I'm saying 3 is the parent of 6. So we got to just go back again to prove that, right? So I take this tree, and you would probably think of doing a tree with pointers. And you would have a pointer as you go up the tree. But we flatten the whole thing out. And you can always get to the parent of any node by dividing its number, that's the index in the array, by dividing that by 2. I didn't, this is a standard trick in the literature, in Knuth or whatever, but possibly one that people don't think about very much. But a binary tree you can implement without any pointers by simply, to go up the tree, you divide by 2, and to go down the tree, you multiply by 2, and sometimes add 1. And so that is a really nice way to save on the data structure. So let's expand this up a bit. This is kind of getting into what does the Go struct look like. So I have a slice of these nodes. The nodes have so these are the sequences, right? These are the 4 sequences of numbers. I've pulled the first number off in each case. So that's the sequences coming in. That's the current value. The losers are stored here. This is the upper part of the tree. And I'm remembering kind of where the number came from, so I can pop the next one off. So that's the tree, the node data structure. The tree data structure is just a slice of those things, right? It's a slice of nodes. And I have one other thing which I call max val. So this is the infinity number. This is not this is not a variable, right? This is hard-coded into the program. So what would be nice is if I could put it here, if I could have it as a type or some kind of parameter to the type. But I can't do that in Go. I can only parameterize types on other types. I can't parameterize types on values. So this is a kind of slightly annoying hack that I have to put it in as a variable because I can't within the language I can't have a value as a type parameter. This is a lot harder than my first talk, right? Those of you who this is really annoying for the video, I guess, because you. Sorry. Okay. Everyone with me so far? Good. Wall of code. I'm not going to go through in minute detail here. What is interesting? So this function is called replay games. This is the kind of main loop of the loser tree with that animation that I showed you earlier. We start at a position, we go to its parent, and we keep on iterating to the parent until we reach 0, which is the top of the tree. If this one wins against the previous winner, then that's now the loser. So we kind of flip them around, and we store the new winning value is this value, and the losing value is what we store. When we come out of the loop, the thing at position 0 is the overall winner. So I think this is remarkably simple code. I mean, you kind of, I suppose another thing that's remarkable is the version on the Wikipedia page is wrong. So anyway, so this is actually remarkably simple. There's no chasing pointers. There's no indirect method calls, right? That was the thing I started with the less and the swap. So we get to do, instead of calling a function called less, we do this, less than, and that means that the Go generic system writes out all of the code for whatever type I use this with, and we don't spend any time dynamically looking up the call. So let's see, how did it work? This is kind of the idealistic way of doing it. So this is on the left. This is what I said was my kind of abstract way of doing it. On the right, this is an interface from inside Prometheus, which is a monitoring system. And there's a thing called postings, which is a funny word that means index for people who write this kind of system. So this is the actual code from Prometheus. So it had an at method, and it had a next method. And this is not entirely an accident, because this is what I was trying to speed up in the first place. It fits, right? I can use this postings thing in my code. I can use the thing called series ref, which is a uint64. I can use that as a value, as an ordered. So that's great. So there's a benchmark for this in Prometheus already. And how did we do? It's, how do you want to count that? It's like between 4 times and 8 times faster, something like that. So I was pretty pleased at that. It does use more memory. So this is this is bench stat. If you've never come across it, it writes out these tables with the percentage change. So the bytes used to do the work goes up. This is because we're constructing that kind of extra. The top half of the tree is the memory overhead. For 100,000 items, that's like 100,000 different metrics in Prometheus. It took 4.5 extra megabytes. I mean, it's nothing. Prometheus is easily using 8 gigabytes at this point. So the extra memory is percentage-wise pretty small. But I mean, relatively, it's massive. Relative to what this one bit did before. Relative to the whole size of the program, it's nothing to worry about. So this was Prometheus pull request 12878, which was merged, I don't know, several months ago. So, chuffed. There was another problem. So let's switch tack completely. I work Grafana Labs, I work on storage of metrics and logs. So I did this other animation I'm going to make you sit through. Just to illustrate the problem, imagine we have logs coming off a bunch of different computers, and they're all kind of emitting logs at different times, right? It's too small for you to read, that's intentional. There's logs coming out at different times, and then when you, as the ops person, want to figure out what's going on, what you want to do is is see it all as it happened. You want to interleave the log lines by their timestamps. Well, at least that's one of the features of the program Loki, which is our log database. And that's the same problem, right? The interleaving of logs by timestamps is the same, is the k-way merge problem. And this problem actually shows up a lot in databases. The thing is, in Prometheus, the postings series ref is literally an integer. It fits brilliantly well with my scheme, my generics. In Loki, the thing that we've got is a log line. It's a string, right? Well, a string and a timestamp. Again, on the left, this is the thing we're trying to match. And the thing on the right is what I've got in Loki. It is not ordered, right? I can't do less than. I can't do less than on the whole log line, and I can't do less than on a timestamp either. I have a slightly different iterator set of methods as well. I don't have an at. I have an entry. And so, yeah, slightly not quite matched. Okay, so we can't just use less than. We can't. We have to give up on that. That's a bit sad. Okay, so can we define a method in generics saying my type has a less method that compares two things of the same type? What do you think? Can we do this? Yeah, nobody puts the question up like this where the answer is yes. Okay. So if you try and compile that, it barfs at you. I'm not entirely sure what this error message means, really. But anyway, okay, different idea. So we're gonna say I can compare this against anything. No. So as at when I wrote this talk like a year ago, I realized that it is in fact written into the spec of generics that you can't do this. No parameterized methods is the section heading. So you're not allowed to do this. Except you are. I got a PR from this helpful person. I mean, that's their GitHub avatar. That's not in the room, are they? No. Okay. Yeah, it turns out what you need to do. So you can use this. You can use the any thing, but you need to bring it up here. You need to say, I have an element type and a value which takes the same type as a parameter. So you kind of recurse the thing in on itself, and now you can have a less method that takes the same type, that compares one thing against another thing of the same type. But anyway, I went with a function parameter. So the bad reason is I didn't know you could do it. And the good reason is that, in fact, in Loki, we can sort forwards or backwards. So when sorting log lines, we pass in a less function, which is actually greater than, right, in order to flip the sort order. And you can't do that with a method. You can't sort of pass in, you can't flip a method or something like that. Anyway. So in order to fit it into Loki, I actually have 3 function parameters. So I have the max val, which is a value that shouldn't be a value. I have a function which probably should be a method, but there are reasons. And then I pass in this one to get the current value, and this one to close the sequence. Think in terms of if you're reading from files or something like that, closing the file. It ended up a lot more indirect. These are function calls through a function pointer, which was the whole thing I was trying to avoid in the first place. So how did that go? So this is compared to the previous version. This is compared to what it got in Prometheus. It is quite a bit slower because it has to do this indirect function call. So just rubbing that home. So this is the same, the inner loop, the replay games method. Because we have to call this function, the processor spends that much extra time kind of figuring out where it is and what it's going to do next and so on. Now, one of the good things about going to San Diego and having Russ Cox sit in my talk and having half the Go team there is they got a little bit interested in how we could make this go faster. So there's a concept in Go called devirtualization. Who's heard of that? Nobody. Okay. So I got to explain just a few concepts. One of them is profile-guided optimization, which is in fact the talk that Michael Pratt is giving in the big room right now. Again, that's less helpful for the video. But what you do there is you give the compiler a profile of your program. And the compiler says, oh, this thing is completely generic, but every single time you call this thing, it's with one of those log entry types. So what the compiler is going to do when it recognizes that is going to write out another copy of the code, hard-coded for that type. So you basically pull this dynamic lookup out of the inner loop. And the compiler checks once at the beginning. It says, is this a log entry? Okay, we'll go down this route. This is the devirtualized route. And otherwise, we'll do the generic, fully generic dynamic dispatch thing. So that's, it should go faster. It doesn't. I filed a bug. yeah. It's basically the devirtualization code in the compiler is not quite clever enough to recognize what is going on here. But in one or two more versions of Go, this will go fast, as long as you use profile-guided optimization. How are we doing for time? Are we good? No idea when I started. Started about 35 minutes ago.
10 minutes, then 15.
Yeah, okay, well, bonus content. So when I was going through this and looking at the basic idea of sequences of data and kind of iterating over that data, iterators? Go 123 has iterators. Has anyone looked at this? Yeah, a couple of people? Okay. So the idea of iterators in Go 123 is that you can do range thing, where thing is something you wrote, something you explained to the Go compiler how to do iteration. So instead of calling next and at, which is what we did in Prometheus and roughly what we did in Loki, we can do for range. So the way you write an iterator is a little bit funky. It's a terrible pun. It's a function that takes another function, and so it gives you this function, and you call this one back for all the values in the sequence. And if you've not downloaded Go 123 yet, you can also use this in Go 122. You just have to turn it on with a Go experiment environment variable. Okay, so let's rewrite loser tree with Go 123 iterators. So we're going to apply this EE trick here with the less function that I got from my friend. Everything else has disappeared. We don't have the next method. We don't have the at method. Nice. Looks a lot cleaner. The basic way that you write an iterator in Go is like this. Go gives you the yield function, and you call the yield function back with values. So in terms of the loser tree, what we're basically going to do is kind of kick things off, and then we're going to run the tournament, replay the games, find the winner, and call the yield function with the winner every time. So that looks like this. The bit I've highlighted is that we turn, so Go iterators are push, right? They have values and they call a function, they push values into the function. I can't really deal with pushing values because what I want to do is pull off k different iterators at the same time, or at different times. So I turn the push iterators into pull iterators. This is the iter.pull is in the Go standard library. So the stop function is something that is this is like the close function I had earlier, and I just defer those all to the end of the function. So this is kind of setting things up. We turn all the push iterators into pull iterators, and then we call replay games. You can look at the detail on GitHub if you really want to, but I mean structurally it's really nice. A lot of the kind of many things I had to write about have disappeared in the structure of the thing. Everything else, in like the actual replay games, for instance, completely unchanged because the data structure of the loser tree is unchanged. Just the way that we step through it has changed. Benchmark? Wah, wah. So this is a little bit sad. Basically, that pull function, which turns push iterators into pull iterators, is really expensive. You do not want to be calling that 10,000 times in your inner loop. The code runs a lot slower. It uses quite a bit more memory, and the number of allocations is astronomical. Well, that's a comparison. So there's 10,000 sequences, right? So there's about 13 allocations per sequence, and they're all in that pull method. It sets up coroutines. I mean, who even knew what a coroutine was? So now you can see why I'm really glad that Russ Cox is not sitting there, because I'm bad-mouthing his code. No, I mean, I'm reasonably sure this will get better in future versions of Go. It might be argued it's just not a very good fit. Go iterators are push-based, and the loser tree, this whole k-way merge thing is pull-based. So it was a fun experiment, and bonus content from much better than the last time I gave this talk. Anyway, don't want to end on a low. Do we have any other benchmarks? So when I plugged the algorithm into Loki itself, which is our logs database, this bit went 30% faster. That's not bad. And a slightly different part of the code went, what is that? That's like 4 times as fast. So really pleased about that. This is the end of my talk. So we looked at the k-way merge problem in abstract. We talked about how the performance suffers from calling through a dynamic dispatch interface. And the loser tree goes, in some cases, a lot faster, in some cases, a bit faster. It is very much leveraging Go generics. They work really well. It is a really terrible fit for Go 123 iterators. But that was fun to find out. And this is what the AI thinks a loser tree would look like. So go figure. Anyway, thank you.
Okay, plenty of time for questions. One here.
It just so happened that I've been writing code to do an external sort and basically using a container heap at the end to merge the chunks together.
All right. Yeah, try this.
Yeah, basically, I was just going to say thank you. Basically, no questions.
It's more of a comment than a question. Yeah.
Next question.
Oh, there's one here.
Do you have any other fun examples of 2 implementations of an algorithm which, complexity-wise, look to be the same? The heap implementation is n log k, the loser tree implementation is n log k, where you have a similar example of n log k is not the same as n log k.
Yeah.
That was worded confusingly.
Yeah, no, I know what you mean. I mean, basically, the algorithmic complexity is not the be-all and end-all of performance. And I think Rob Pike said simpler algorithms work better when n is small, and n is usually small. So I would say, in terms of examples, I think sorting. In fact, this is in the Go code if you're sorting hundreds of things, it's broadly using quicksort, but it sorts down to a certain level of, when it gets down to like 10 items or something like that, it uses insertion sort. So it switches from a complicated algorithm to a very simple algorithm when n is quite small, and actually does this dynamically in the running of the function. What I just said is not absolutely accurate because they changed the algorithm 2 versions ago, I think. But yes, it is a general pattern that doing like less clever stuff, particularly less pointer chasing, especially less memory allocation. I mean, this is about a bit of an outlier for me because I'm doing more memory allocation, and I do tell people that the problem is always memory allocation. But yeah, less pointer chasing, less memory allocation might go faster if what you're doing is basically simpler. I was talking to someone earlier who reminded me of a phrase, mechanical sympathy. And I quite like that phrase. And so the basic idea is that if you have a bit of an understanding of how the machine works, you will be able to drive it better. It literally came from racing drivers, the idea. But in terms of a computer, understanding a bit about how the CPU works and how the caching inside the memory of CPUs works and the things like branch prediction. So yeah, these are all things that basically go to why is it really faster? It is a simpler structure. I mean, that's certainly a way to understand it, and it is doing less pointer chasing, but also it fits the internal structure of a CPU quite nicely. And that sort of concept of mechanical sympathy is there, that it's a better fit for the machine. There you go. Very philosophical answer to your question.
Brilliant. Next question.
That's floored everyone.
Anyone keen? Okay.
Now extra time for coffee. Anyway, thank you all for coming.
Thanks, Bryan.